Okay, so we were on course to prove structure theorem for Artinian rings. It says that an Artinian ring is uniquely up to isomorphism a finite product of Artinian local rings. So, yesterday what we proved was that if we start with, if A is an Artinian ring with the maximal ideals so we know that Artinian rings have only finitely many maximal ideals. So, if A is an Artinian ring with the maximal ideals m1 up to mk, then some mn, then we showed that A is isomorphic to A mod m1 power k cross A mod mn power k for some integer k, right. This is what we showed last time. So, now what we want to show is that this is unique in the sense that if I take any product, if A is isomorphic to some product of Artinian local rings, then they are, those AIs are uniquely determined. Okay. So, let us let A be isomorphic to product of AI I from 1 to m for some Artinian local rings A1 up to am, and for some Artinian local rings A1 up to am. Now, what we want to show is that this AIs are uniquely determined. It has an independent structure irrespective of this has an independent structure coming out of A. Okay. So, let us look at this map. Let phi I be the map. So, this is A1 cross A2, this is A1 cross up to AM. I can, so this is an isomorphism, and I can compose the isomorphism with projection onto AI and call it phi I. If A to AI be the projection onto the ith component. Okay. And let II be equal to kernel phi I. Okay. Now, this AIs are Artinian local rings, which means AI has only one prime ideal, which is also maximal, and this has only one maximal ideal, but any prime ideal of an Artinian ring is maximal. Therefore, AI has only one prime ideal. So, let Ni be the unique prime equal to maximal ideal of AI. So, therefore, this is Ni itself is nil radical of AI. AI is Artinian local, therefore, it is Noetherian, therefore, nil radical is nilpotent. That means, Ni power some R I is 0 for some R I in N. Now, suppose I take, let P I be the inverse of N I in A. So, therefore, this is prime, P I will be prime ideal and hence maximal ideal, because A is also an Artinian ring. P I is a maximal ideal. Okay. Now, see, N I power R I is 0. That means, if I take P I power R I, an element in P I power R I will be mapped inside, by phi I it will be mapped inside N I power R I, but that is 0. That means, P I power R I is contained in the kernel of phi I. That is, P I power R I is contained in I I. Now, P I is a maximal ideal whose radical is whose power, some power is contained in I I. Therefore, I I is primary to, it is a primary ideal, primary to the ideal P I. Okay. So, this implies that P I power R I is contained in kernel phi I, which is I I. This implies that I I is P I primary, again because P I is maximal. Okay. So, this implies I I is P I primary, and one more thing, what is the intersection of I I? Intersection of I 1, I 2 up to I m, what is the intersection? This is an isomorphism. So, if I take the map, if I take the map x going to x 1 bar, x 2 bar up to x m bar, or x 1, x 2 up to x m here, the kernel is precisely the intersection of all I I's, but that is 0 because this is an isomorphism, right. So, therefore, moreover, intersection of I I is 0 because this is an isomorphism, and this is and precisely the composition with the projection. So, if phi sends A to x 1 x 2 up to x n, this is phi I is A, so phi sends x 2 x 1 up to x n, then phi I of x is x 1, phi 1 of x is x 1, phi 2 of x is x 2, and so on. So, the kernel is precisely the intersection of all this, and that is 0. Now, 0 is equal to this intersection, and each I I is P I primary. That means, this is a primary decomposition of 0 in A. So, this since P I is, I I is P I primary, the 0 equal to I intersection of I is a primary decomposition of zero in A. See here, see if you look at this, phi I is A composite with the isomorphism composite with the projection, then AI is isomorphic to A mod II, but that does not say that AIs are uniquely determined. But if we say that this IIs are uniquely determined, if we can describe II without the help of this isomorphism. Here we are, AI is isomorphic to A mod kernel of this map. That does not give any description of II without mentioning about this relation. If I can describe II without mentioning about this relation, that means it is uniquely determined. Without any other information, without using this information, if I can describe II, that will imply that AIs are uniquely determined. Now, what we have concluded is that all these IIs are nothing but, the IIs, using this IIs I can give a primary decomposition of 0, but again a primary decomposition is not unique, right. As we saw in kxy, the ideal x square comma xy, it has infinitely many different decompositions. So, that does not uniquely determine the components, but later we proved one kind of uniqueness, the first uniqueness theorem, which said the second uniqueness theorem, which said some primary components are uniquely determined. The primary components associated with the isolated primes. See, in the primary decomposition, so I have an ideal I1 intersection, so let Q1 intersection Qm, they are all primary ideals, the radical of Qi, let us say Pi. Okay. Now, if P1 up to Pr, if these are the isolated primes, that is the minimal primes in this, there are minimal prime ideals and embedded, isolated prime ideals and embedded prime ideals. If these are the minimal prime ideals, isolated prime ideals, then Q1 up to Qr are uniquely determined. They are unique in any decomposition, in any primary decomposition, those Q1 up to Qr have to be there. This is what we proved some time back. So, now coming back to this case, let us look at this primary decomposition. Do we see some isolated or embedded components here? What are the primary, what are the radicals of each II? It is Pi. Now, what can we say about Pi? Pi's are all maximal. So, there cannot be an embedded, there cannot be a prime ideal that contains Pi, right. There cannot be a prime ideal that contains Pi. So, all these Pi's are isolated. They are all isolated means each II is uniquely determined. That means AIs are uniquely determined, because what we need to do is, what we are proving here is that if you take a primary decomposition of an Artinian ring, if you take an Artinian ring and look at a product, then this product cannot be too different from this product has to be of this form, where you look at the 0 ideal in A, look at its primary decomposition. In the primary decomposition you will have only isolated primes, because you take any primary decomposition, each primary ideal will be primary to some prime ideal, but every prime ideal of A is maximal. So, therefore, you cannot have an embedded component there. So, look at look at the primary decomposition, look at each component, that is nothing but, and therefore they are each primary component associated with the unique associated with the isolated primes are unique. So, take those unique take that unique primary decomposition, each AI has to be A mod II for some ij, II. That is precisely what we are proving here. Okay. So, let me complete this. Since radical of II equal to Pi is maximal, Pi's are isolated primes associated to 0. Therefore, the primary components IIs are uniquely determined. That means AI isomorphic to A mod I are uniquely determined. Okay. So, that proves the structure theorem. So, up to isomorphism. So, in an Artinian ring, what you need to do is look at 0 ideal, look at its primary decomposition, okay, and look at look at any primary decomposition, because any primary decomposition will be the same, because all the components are all the primary components are primary to maximal ideal, therefore, they are all isolated, there are no embedded components there. So, therefore, the primary decomposition is unique. In that primary decomposition, look at take the I1 up to IM, A mod IM, A is isomorphic to A mod I1 cross up to A mod IM. Okay, that is precisely an Artinian, how an Artinian ring looks like. Okay. So, we were talking about, see, Artinian ring is same as Noetherian ring with all maximal ideals, all prime ideals maximal. Okay. So, this property that all prime ideals are maximal has another name called dimension 0. So, what is dimension? Dimension is, this is called Krull dimension. If you take a chain, so this is let A be a ring, okay. The length, so then dimension of A is by definition maximum of n such that there exists a chain of prime ideals P naught prime ideals of A if there is a look at all n for which there is a chain like this and look at maximum. Okay. 0 need not be a prime ideal, right? Okay. For example, what is dimension of K field? It will be 0, right? There is, because you do not have, there is only one prime ideal which is 0 itself. If R is, if A is a PID, then dimension of A is, see, if you take any integral domain, you can always start with 0. 0 is a prime ideal. Now, what will be the next prime ideal? It should be a non-zero prime ideal. In a PID, a non-zero prime ideal is maximal. So, you cannot have another. So, therefore, dimension of A is 1. Can you give me another example where dimension of dimension is 0? If you take an Artinian ring, or for example, Zn if you take Zn, it is going to be an Artinian ring, right? If n is, how do you say that this has dimension 0? If n is prime, then it is a field. If it is not, what are the prime ideals of Zn? See, this is nothing but Z mod Nz. What are the prime ideals of Z mod Nz? P Zn where P divides n, right? Now, they are all maximal. They are all maximal in PZn. So, therefore, the only prime ideal here you can start with is P naught, there is nothing more. So, therefore, these are all. Can you generalize this looking at, I mean, can you from A take A and bring it to an Artinian ring? What is that we are doing here? Z is a PID, right? So, what is that we are doing here? If I take A be a PID, okay, can you construct an Artinian ring from A? How do you get an Artinian ring from A? It should be, PID is Noetherian, right? So, every prime ideal should be maximal. Now, what are the prime ideals of A? Non-zero prime ideals are all maximal. Everything is every ideal is generated by one element. A mod P power n for some n, P is prime element in A, no, when you say prime element, it is already non-zero. This is, see, the only prime ideal that contains only prime ideal that contains p power n is the ideal generated by p. So, you have only one prime ideal in such a chain here, right. There is only one prime ideal here, but can we say more? Is it necessarily be of this form? See, for example, Z6 is this Artinian?
Some power of P1 power n, P2 power n2.
Okay, so more generally you don't need to say even powers. F non-zero, right? This is going to be Artinian. Why is this Artinian? What are the prime ideals of this? The prime ideals of this ring are prime P which contains F. Now, what are the prime ideals that contain this F? F is in A non-zero, F is in a PID, therefore, it is in a UFD. F has a primary prime factorization. I will write this as F1 up to Fr. Then the prime ideals of I call this B. Prime ideals of B are precisely F1 mod F, F2 mod F and Fr mod F. These are the only prime ideals of, but they are all maximal, because this is generated by an irreducible element. They are all maximal. So, therefore, the only prime ideals of B are generated by F1 up to Fr and they are all maximal, hence B is Artinian. Then the prime ideals of B are F1 bar, Fr bar. Since B mod F1 bar, this is isomorphic to, this is equal to A mod F modulo F1 mod F, which is isomorphic to A mod F1, which is a field, because F1 is an irreducible element, non-zero irreducible, I mean it is an irreducible element, therefore, this ideal generated by irreducible element in A is maximal, therefore, this is a field. So, therefore, these are all maximal ideals. That means, every prime ideal in B are maximal. B is Noetherian because A is Noetherian. This implies B is Noetherian and every prime ideal of B is maximal. This implies B is Artinian. Okay. Now, let us look at one more nice property of Artinian rings. Let A be an Artinian local ring with the unique maximal ideal then the following are equivalent. every ideal of A is principal M is a principal ideal dimension as an A mod M vector space, the module M mod M square. Here what we are saying is, in an Artinian local ring, if the maximal ideal is principal, then every ideal is principal. An Artinian local ring is a principal ideal ring if and only if the maximal ideal is principal. Okay. So, one implies 2 implies 3 is straightforward. 1 implies to every ideal is principal implies M is principal. Now, if M is generated by one element, then this is by Nakayama's lemma. Okay. 2 implies 3 is straightforward application of Nakayama's lemma. So, 1 implies 2 trivial, 2 implies 3 follows from Nakayama lemma. So, let us prove 3 implies 1, that is, the vector space dimension of M mod M square is less than or equal to 1 implies every ideal of A is principal. So, let first of all, if dimension A mod M of M mod M square, suppose this is 0, what does that mean? If this is 0 means that M has to be equal to M square. A vector space, if it contains one non-zero element, it will have dimension at least 1. So, this is 0 means M has to be equal to M square, but again by Nakayama lemma, if we are in a Noetherian local ring, M is finitely generated. So, therefore, by Nakayama lemma, M is equal to M times M, which means M has to be 0. And M is 0 means what? K is a field, right? That implies I mean A is a field. So, therefore, we can assume that now let us assume that dimension of M mod M square is 1. Now, we are in a Artinian local ring, M is the sorry M is 0, A mod M is always a field, right. For any maximal ideal, A mod M is a field. Now, M is 0 means A mod M is same as A, or these are characterization that we have discussed earlier. A field is nothing but maximal ideal being 0. So, suppose let M be generated by some element x. Okay. A is an Artinian local ring and M is the maximal ideal there. Now we need to prove that every ideal of A is principal. So, let us start with a non-zero ideal. Let I be a non-zero ideal, an ideal of A. We want to say that I is generated by one element. Okay. Now, M is the unique maximal ideal in A, therefore, the nil radical of A is m, nil radical of A is nilpotent, therefore m power r is 0 for some r, right. What does that mean? Since A is Artinian, local, m is nilpotent. That means m power r is 0 for some r in m. Huh? Sorry? This one, Nakayama lemma. If m, if dimension of m mod m square, so we proved this. If as a vector space over A mod m, if m mod m square is minimally generated by x1 bar, x2 bar up to xr bar, then m is generated by x1 up to xr. This is something that we proved immediately after Nakayama lemma. So, this implies, in fact, these two are equivalent, 2 3 are equivalent is known long back. The main contribution here is that they are equivalent to every ideal being principle. So, m power r is 0, that means, see, I is not contained in m power r. Okay. So, therefore, look at the least, see, I is contained in m, m is the unique maximal ideal. So, every ideal is contained in m. Now, look at the least n, let T be in n be such that I is contained in m per t and I is not contained in m power t plus 1. Okay. See, I is contained in m and m power r is 0 and I is non-zero. That means there exists some positive integer such that I is contained in I is not contained in m power t and I is contained in m. So, I look at whether I is contained in m square. If I is contained in m square, look at check whether I is contained in m cube. If it is not, that 2 is the 2 is equal to t. Similarly, we look at the least integer for which I is contained in m power t, not least integer, the largest integer for which I is contained in m power t. So, therefore, this implies that I is contained, what is, but what is m power t? M power t is ideal generated by x power t. Now, yeah, so I want to say that I is contained in x power t, x power, so I is not here, yeah, since I is not in m power t plus 1, there exists y in I, but y is not in m power t plus 1. Okay. That means, now y is equal to a, yeah, y is equal to a x power t for some a in a, because y is in I and I is contained in x power t. Now, can A be in the maximal ideal? Maximal ideal is generated by x. Can A be in maximal ideal? See, if A is in maximal, it will be equal to some A prime x, which means y is prime x power t plus 1, that will imply y is in m power t plus 1, but our assumption is that y is not there. Therefore, since y is not in m power t plus 1, A is not in M. But what are the elements which are not in M? In A, this is the unique maximal ideal. So, if it is not here, then A is a unit. This implies A is a unit, and that would imply that x power t belongs to I is contained in x power t belongs to I, that will imply that I is generated by one element which is precisely x power t. So, y is equal to A times x power t. So, A times x power t is here, is in I, y is in I. So, A times x power t is here, A is a unit, any multiple of this is here. So, multiply by A inverse. See, this is somewhat clear. What are we doing here? We are looking at, we are taking an arbitrary ideal. Okay. We are starting with an arbitrary ideal, that ideal is contained in M. Okay. Now, we look at the largest integer such that I is contained in m power t. So, I is contained in x power t. Now, every element of I is I is not contained in x power t plus 1. I is contained in x power t, ideal generated by x power t, and I is not contained in ideal generated by x power t plus 1. Every element of I is some a power t, a into x power t, but then a cannot be in M, because if a is in M, that will imply that y is in x power t plus 1. So, therefore, a has to be a unit, which means I has to be generated by this x power t. So, every principle, every ideal is generated by some power of the maximal ideal. Okay. So, examples like, well, not all Artinian local rings satisfy this property, but for example, if you take kx mod x power n, okay, I mean of course zn, you take any zn, that will satisfy. If I look at an example where this is not satisfied, an Artinian ring whose maximal ideal is not a principal ideal, that x square x cube x power 6 this is an Artinian, so this is Artinian rings with maximal ideal principal these are, now if you look at k x y mod x square x y y square, these are Artinian rings with maximal ideal, not principal. Here the maximal ideal is generated by x and y, here the maximal ideal generated by x square and x cube. We will prove what are one of the most important results in commutative algebra that has large implications in important implications in algebraic geometry, called Noether normalization and Hilbert's Nullstellensatz. So, before this, let me just recall some basic facts. Suppose I have a ring homomorphism from A to B. Okay. This is a ring homomorphism. Then correspondingly I have a map f star from spec B to spec A. What is spec B? Set of all prime ideals of B, and this is set of all prime ideals of A. So, what is f star of P? F inverse of P, right, that will be a prime ideal here. So, therefore, this is okay. Now, see, we were talking about integral dependence, integral extension and so on. So, what we showed some time back is that if I have an integral extension, and if you start with a prime ideal here, then I have a prime ideal here which intersects with A to give P. This is called lying over theorem, right. The first one we proved, given any prime ideal, there exists a prime ideal lying over this, okay. And then using this we proved the going up theorem, okay. So, now suppose you take, so see in geometry one thing is that when you are studying, when you want to study curves or geometric objects, one way is to reduce them to a slightly simpler situation and then study. There are many ways of, one of them is, so one way is, one thing is, suppose I have a suppose given, so I have an algebraic set for which I have an ideal I. So, I have this polynomial ring k x 1 up to x n. This is called the coordinate ring of the variety V. So, this is corresponding to variety or algebraic set X. Now, if you look at this ring, one of the questions that are relevant in geometry is whether this is a finitely generated module over some polynomial ring, okay. So, this is indeed true is what the result Noether normalization say. We indeed have a we have any finitely generated, so any finitely generated K algebra looks like this, k x 1 up to x n modulo some ideal. So, the Noether normalization theorem says that this is indeed true, and we will precisely say what can be in some nice cases what are these z 1 up to z r's. One can take this as some linear combination of xi's. Yeah, so I will do this in the next class.